True story. I was employed in high school as a watch repair technician. In fact, I can still replace batteries in most non smart watches. Back then, coin cell batteries were mostly regulated to watches and backup batteries for PCs. But today, from key fobs to IoT devices, they are just about everywhere. But they do have their downsides. They need to be replaced often. They can be rather impractical. And don't even get me started on how much waste they cause. So, is the solution to replace all coin cells? Probably not. But if we could extend their lifetimes, that would sure help a lot. Hi, I'm Amelia Dalton, host of Chalk Talk. In this episode of Chalk Talk, Tom Wolfe from Nexperia and I examine how Nexperia's battery life booster ICs can not only extend coin cell battery life, but also increase the available power of these batteries and reduce battery overall waste. We also investigate the role that adaptive power optimization plays in these ICs and how you can get started using a Nexperia Battery Life Booster IC in your next design. And before we get started, don't forget to click that link. There you can find even more information about this topic from Nexperia. Hi, Tom. Thank you so much for joining me.
Hello, Amelia. It's always good to be here at Chalk Talk.
Excellent. Okay, so we're talking about how we can stop changing batteries. But, Tom, are we talking about some kind of perpetual energy type of thing? Or what exactly are we talking about today?
That would be really good. No, what we're challenging you to do is to stop changing your battery so inefficiently and wasteful the way that you're doing today. What we want to talk about today is Nexperia's new battery life booster, which makes it way more efficient to use those coin cell batteries in your application. So the best way then is to get started with exactly what is a coin cell in the first place. You guys have all seen them before, but just a quick overview. Matter of fact, where do we see coin cells at the most often? And probably the place you see it the most often is in your key fob for your car. It's the remote control that starts your car up today. They're also in your car, probably in your tire pressure monitors. Some are rechargeable, but most of them, there's a coin cell buried in each one of the tires of your car as well, too. And we see them in consumer electronics also. They're in smart tags, that little disc you can use for tracking to see if your luggage is going to a more fun place than you are when you go on vacation. So they show up in applications like that. They're in wearables. They're in all sorts of exercise bands, in smart shoes and heart rate monitors, medical equipment like glucose monitoring. It's that little coin cell that fits in that small consumer product. There's not enough room for like a big AA battery. So you use a coin cell for it. They show up in remote controls as well, too, particularly the little small ones that are like the size of a credit card, not your big TV remotes. So you'll see them in consumer applications all the time. But the place you're probably not aware of is they're used extensively in the industrial and the sensor market as well, too. For things like asset tracking. You ever wondered how they know when a package gets from one place in a truck across the country to another? There's asset tags on all those valuable things. On the shipments that are in trucks and on planes and in cars, there's an electronic tag with a coin cell battery that's monitoring where it is it on time, did it get lost, was it tampered with, did the temperature of the frozen fish stay cold like it's supposed to? So they're used extensively in that marketplace. They're also used in things like building automation. Up in the ceiling of your office, there may be a number of these sensors, 50, 100 of these little sensors scattered around to determine that the temperature of the air conditioning's fine, that the dust and the pollution are fine. So there's a lot of these batteries used in applications that as a consumer, you might not see. But from an industrial point of view, there's a lot of these batteries used in all sorts of applications today. Now, what's the problem with coin cells? Well, the problem is that coin cells, as we use them today, were never intended to be used for that. Originally, they were invented to be used for a low amount of power over a long period of time. In fact, anybody that's been in the computer industry for any amount of time will remember when you had the coin cell on your motherboard inside your PC. It was there to back up the BIOS, to back up the settings of your PC. Every once in a while, you had to change the battery because your computer would wake up and forgot who it was. So that was an application where it was backing up memory, a small amount of current for a very long period of time. Of course, the other one too is kind of their nickname. They were used in watches, in wristwatches. We sometimes call them watch batteries. Now, the CR2032, which is the main battery used for asset tracking, that's a much bigger battery, but it does show up in some of the big watches as well too. Again, though, that's an application where it's used for a low amount of power for a long period of time. The problem with today's applications, all those ones we've been talking about for your key fob and your temperature sensors and things like that, is that the battery is now being used for a high pulse current in a short period of time, which is not what it was designed for. Again, it's like when your key fob, it doesn't do anything for a long period of time until you want to unlock the door, you hit the button, and it sends out a burst of energy to transmit across the parking lot to your car. Those alarm sensors and temperature sensors may sit and wait for hours, minutes, days sometimes, and then do a burst of energy. That is not what those batteries were designed for, and that's where the problem is.
All right, that makes sense. Now, Tom, what's the issue with these coin cells?
The issue with that then is that using the battery in this mode, this stresses the chemical makeup of the cell, which greatly decreases its lifetime. In other words, you're killing the battery because you're not using the way that it was originally designed. What we want then is a solution to make the battery fit into the applications that everybody's using it for anyway. So let's look at coin cells from a performance point of view, because they've got a lot of advantages. The first one is that they're energy dense. Now, compared to like an alkaline battery, your double or triple A batteries, you're getting more power per cubic centimeter of space of the battery. So there's a lot of energy packed into a very small space. That's why everybody likes using them. And they're relatively low cost. You do these in bulk pricing and they're a dime, 15 cents, probably cheaper when you buy them at higher quantities than that. So they're very inexpensive, particularly compared versus rechargeable batteries, which have a limited number of cycles. So those are the pluses for coin cells. Here's the downsides of them though. The chemistry of the battery itself gives it a high internal resistance, about 10 to 100 ohms. Other battery types like the AA's and AAA batteries you might be used to, they're less than an ohm. What that means then is that inside the cell itself is additional resistance. So whenever you pull power out of the cell, it has to go through that internal resistance, and the resistance causes a voltage drop, which means you're wasting energy. So think about it. The more power you pull out of a coin cell battery, the more of that energy you're wasting in the first place. It literally was designed for a small amount of power over a long period of time, not a lot of power over a short period of time. And then that's what gets to the real problem with the cell itself. When you pull these high current loads above 10 milliamps or so, and the higher you go, the worse it gets, you are depleting the electrolyte. You are chemically changing the battery inside. You're using it up, and that's what, of course, ultimately results in a shorter lifetime for it. So there's a couple charts here on the page. On the left side, you can see voltage versus time. So the battery has a nominal voltage, 3.0, 3.3 volts, depending on the device itself. When I put a load onto it, the voltage drops because there's that resistance inside the battery itself. So the voltage drops from that nominal 3.3 volts down to 2 volts or 1 volt, depending on how big the load is. Then the chemical reaction starts taking place. The electrolyte inside the cell is being used up to provide the energy that you need for getting the power out of the device itself. When you remove the load from it, of course, the voltage springs back up. But it doesn't spring back up immediately. You don't get all the way back to the full nominal voltage the instant you take the load off. It takes a while. And that's what the chart on the right side is showing, that depending on how hard you hit the battery, how much power you take out of it, is going to tell you how long it's going to take until the battery recovers and is back to that original voltage to do the next job that's coming down the line. So again, coin cells are not really built for the types of application that everybody really wants to use them for today. And that's why we're looking for a better solution for it. So what this means then is that coin cells have to be replaced often. And there's a lot of disadvantages to that. First, it is impractical. Now, I don't know about you, but it seems that the coin cell battery in my car remote, it always goes out the day it's raining and I'm standing in a parking lot trying to get the thing to transmit. Now, that may not be the same for everything, but in reality, if I'm using these in an industrial application where I've got 50 of them up in the ceiling of an office building someplace, odds are one of them just isn't going to go out at one time. Do I want to send one technician out with his van, his ladder, climb up in the ceiling to replace one battery? No, I'm probably going to want to swap a whole bunch of them or all of them at the same time because that service cost is so expensive. What this means then is that I'm limiting the life of the battery itself. Again, if I'm going to have the technician come out and swap all 50 of them, well, some of the batteries have died already. Some of them are still good, but I'm going to take them all anyway. I'm going to throw away the bad ones. I'm going to throw away the good ones. I'm going to replace them all with brand new ones. And by the way, batteries don't all wear out at the same time. There's chemical differences between them. So odds are I'm throwing away good batteries. But the worst thing is that some of those batteries probably already failed before my technician came out. In other words, I may not have had security in one part of the building because its battery died a week before the technician came out, or I don't have fire protection on it. So it really limits the functionality of these devices by having them fail at an indeterminate time. What this means then is that I'm adding a lot of cost into my overall system. I've got the maintenance cost. The guy has to drive out and go up in the ceiling and do the work on it. I have to manage all the swaps for it. So here's the key thing. This device from Nexperia is not meant to offset just the cost of the battery itself, that nickel or dime or whatever it costs for the battery. It is to add efficiency to the entire system that you have. It's to help you remove the cost of that technician coming out and all the overhead costs that come associated because that small, cheap battery failed. We want to get rid of the other costs associated with it as well, too. What it really boils down to, and really the challenge of this presentation, is it's so wasteful. We're throwing away batteries that aren't already burnt out. We may be missing batteries already died, and we're losing the efficiency of our system because we didn't have a battery and a sensor that we needed. Most of these batteries are not being recycled. Hey, when you changed your key fob, you probably threw it in the garbage. You probably didn't take it to a recycling center. So what it comes out is that we're throwing away a huge number of these batteries. The current estimate says by the year 2025, we will be throwing away upwards of 78 million batteries per day. Huge number of these coin cells are being manufactured, all the mining and all the material that goes to making them, and then we're throwing them away. Wouldn't it be great if we could make these batteries last a whole lot longer and reduce the cost of the entire system? That's what we want to do.
Absolutely. Tom, that seems like a whole lot of wasted batteries. Let's talk about how we can fix that.
Exactly. So, what we need to find is a more user friendly, durable, and sustainable way of energizing these low power devices. There's going to be more and more devices made all the time. We can't just ignore them. We have to find a way of solving this coin cell battery solution, making these things last longer than they were ever designed in the first place. So, with that, let's look at Nexperia's solution for this, which we call the Battery Life Booster IC. Now, these were the objectives of the device itself. We wanted first to boost the available power in the device. You may have noticed before, when you start pulling more than about 10 milliamps out of a coin cell battery, that internal resistance becomes significant. You start boiling off the electrolyte. That's when the damage, when the use of that battery really occurs. Well, we would like to get 200 milliamps out of the battery. That's way beyond what the chemistry can do. So can we build a chip which will allow you to draw way more power out of the battery than you could just connecting the battery directly? And second, here's the hard part, we want to boost the battery life as well too. We want to make it more efficient how the power has been transmitted out of the battery itself into the application, and we want to make this battery last longer. Our goal is to make that coin cell battery last 10 times longer than it would when it's being used in the way that's being used today.
Fantastic. Now, Tom, by extending the battery life, it seems like this would help contribute to less wasted batteries. Can you tell me a bit more about how that really works and the technology behind it?
Yeah, let's take a look at how this magical chip actually meets these two particular goals. So what we want to talk about, we call it the NBM, which is part of the Nexperia battery management system. It is an application-specific standard product. Now that's a big word, but what it means is that this device was designed to solve exactly this problem. This is not a general purpose device. This isn't a microprocessor you can program and do anything you feel with. No, it was built to manage coin cells and batteries that are of that ilk, not just the 2032, but ones similar to it. So it is not just a general purpose DC to DC converter. It has one on board, but you don't just use it for any old conversion that you want. It is not a battery charger. This does not try to put energy back into the battery. Now, you could use this battery booster with a rechargeable coin cell. It really wasn't intended for that. And because of that, it's not going to try to charge the battery. That is not the trick that it uses to make the battery last longer. And it is not a general purpose fuel gauge. Now, it has a fuel gauge on board, which is useful about that old problem of is the battery dead or not? Wouldn't it be great if the battery could tell you how much energy is left in it? So that feature is inside the booster itself, but it is not meant to be used as a general purpose application. Literally, this device was built to handle that issue of the common application where a coin cell battery is being used to transmit data, usually by RF, in burst mode. We want to take this battery and make it being useful for something that it was really never designed for in the first place. Now, the first part of the solution then is something called capacitive discharge. Now, capacitive discharge is a known concept. What we've done is we've integrated it inside this device with other features as well too. Now, to explain what that is, if you've ever been to a water park, there's all kinds of water squirting around and you get wet from streams of water. But there's always one attraction there where there's this gigantic bucket way up in the air, and this hose fills the bucket up, and it takes a long time. You're standing there with your kids underneath it, shivering, waiting for the bucket to drop. You don't know when it's going to be. That is exactly the same as what capacitive discharge does. The Nexperia battery booster is taking a small amount of current out of the battery, which is what it likes, and it's storing it up in a large capacity so that it can dump it all at once. It's being stored in an electric capacitor in this case. So it's exactly the same analogy. I'm taking a little bit of energy over a long period of time and storing it up. Then going back to the analogy, once that water bucket gets totally filled up, boom, the whole bucket tips over, you get totally flooded, everybody gets knocked over, you all laugh and have a good time. That is exactly the same thing the battery booster does. When I need to transmit that radio frequency to tell you to unlock the door or to send that temperature number from the device itself, when I'm ready to send that information out, I dump all that information at the same time out of the capacitors and I get all of it at one time. So I've given the application the energy the way that it wants, a burst all at one time. But from the battery's point of view, I only took a small amount of electricity out of it over a very long period of time. That is the capacitive discharge feature of this device. The second part of it is we have a low input voltage DC to DC converter on board. As we talked about before, as you use the battery in a high load application, the voltage drops. It's no longer 3.330 nominal volts. When you put a load on it, it drops down to 2 volt or 1.5, depending on the load. So what we've added on board the battery booster is a DC to DC boost. In other words, if the voltage drops to 2 volts at the battery, this converter will boost the voltage back up to the 3 volts or the 1.8 or whatever voltage you want it to be. In other words, your application doesn't know that the battery is browning out because of a heavy load on it. So I can make the battery last much longer. If the battery is down to 2 volts, the end application doesn't know it because this DC to DC converter does it on board. It makes up for that missing voltage. Now, both of these techniques are known already in the power supply industry for monitoring power. You can put a DC to DC converter on board, and a typical cycle is, the numbers on the chart here, you can get about 3,500 transmit cycles by adding a DC to DC converter to your coin cell battery. That's really good, okay, on top of what it could normally do by itself. If I put the capacitor on board as well too, the capacitive discharge, the water bucket, if I add that feature, I can get about 4,200 transmit cycles out of it. So those two features independently already increase the life of the battery. However, the Nexperia device is the first time where we've combined both of those features, both of those benefits in the same device by having both capacitive discharge and an onboard DC to DC converter. We can get 29,000 transmit cycles in exactly the same application. That is 7, 8, sometimes 10 times as much life out of the coin cell as you could without having it on board. That then is the benefit of this device itself. It uses a couple of really interesting electronic features to make the battery last much longer than it would if you just connect it directly the old way.
So, Tom, give us some details about this battery life booster.
So let's look at the data sheet, the overview of the device. The full data sheet is available, of course, but it is the NBM 7100 A/B we'll talk about first. There's another version in a second. We call it the battery life booster with adaptive power optimization. Remember those end words because that's actually a key feature we want to talk about. It has not only the ability to do DC to DC conversion and to do capacitive discharge, it learns from your application how you're using the power, and it modifies itself in the charging circuit. I'll show you that in a little bit further on. I can set how much constant battery load I want to have on the device, on the battery itself. It allows me to program the constant battery load from the battery itself. Remember, the lower the current I pull out of the battery, the less it's stressed and the longer it lasts. So I could say, only take 2 milliamps out, just barely pull power out of it, or maybe I set it higher. You choose how much you're drawing out of the battery, which essentially affects its lifetime. Then I can dump a maximum load out of the device of up to 200 milliamps. So I can take a little bit of current over a long period of time and then dump it in all one big burst. It has to run in standby mode. It's usually less than 50 nanoamps when it stands by. So it's sitting there. It has to do its work and do monitoring and stuff, but it's very low power when it's not actually transmitting information out. The converter on board is efficient of about 90%. We've got an integrated fuel gauge on board, which allows you to know what the state of the battery is, to give information like, do I need to change it and things like that. And it comes in a variety of high-tech packages and it operates across the entire temperature range, minus 42 plus 85, which is pretty much where all these industrial applications sit at. So here's a block diagram of it then. Starting in the lower left side, we've got the startup optimizer on board. Remember, this thing has to start up somehow, as it has to actually begin charging the capacitor. So there's circuitry on board to start charging the circuit to become alive and start doing this function. We have a control bus on board where you've got two different options of the interface to it. You can use the standard I2C interface, which is very common in power management and all sorts of computers and application, or you can use the SPI interface, which is a common interface on most microprocessors. That's really the biggest difference between the A and the B version on them. There's a control engine on board, and you can set this part up to either be in on-demand mode, which means it just sits and waits until you tell it to start charging, and then so many seconds later, dump all your energy. Or it can be a continuous mode, where you say, you stay on, monitor the power that I'm using, and always have this much energy available when I need it every 5 seconds, 30 seconds, every minute, or whatever it is. So there's intelligence on board that you can either say, this is when you discharge, or it can actually monitor and work all the math out backwards to know when it has to start filling that bucket so that it's ready when you need it. Of course, it has an integrated power switch on board, something which dumps that load off to the end circuit itself when you need it. I've got programmable output voltage, so I can set the voltage on the output side for 1.8 or 3.6, regardless of what the input battery voltage is. I automatically adjust it so that the application always sees the voltage that it wants. And then finally, external to the device itself is the energy storage element. And that's really the place where you have variability in the design. It's the capacitor you put on the outside. The number of capacitors and the size of the capacitor tells you how much energy I can store up. And then the neat part of it is that there's only a single inductor needed. Most designs, if you're trying to do a capacitive discharge and a DC to DC converter on board, you need multiple inductors. Because the way this device is integrated, you only need one inductor on the outside of it. So there it is, a very small, efficient system for overcoming those limitations of a battery, all packed into one system, ready to go. Let's look at its other variation as well, too. That was the NBM 7100 we talked about. This is the NBM 5100. It's easy because it's virtually the same circuit. However, it has been optimized for the use of electric double-layer capacitors or supercaps. So these are very small, high-energy capacitors. Their limitation is they're based on 5.5 volts. So in the 7100, I can use less efficient but bigger capacitors. For this one is really built for smaller, more efficient capacitors. Other than that, it has most of the same features on board. So there's a variety of different parts depending on exactly what your application is. And here's the block diagram for it again. The only thing that really changed on it is the energy storage element. So I can support supercap devices on it. And what's interesting is I can support 2 of these supercaps on board. And I've added onboard active balancing to make sure that the charge in each one of the 2 circuits, in each one of the 2 capacitors, stays the same. So I'm constantly monitoring that. Other than that, though, the 5100 is basically the same as the 7100, just a different storage element on it.
Okay. So I think I'm getting a good grasp on how these chips work. But can you remind us what the differences between the 4 of them are?
And that's probably the best thing to do. So let's look at this chart. Here are the 4 variations which are available today. Yeah, there's others in design, but these are the 4 we want to talk about now. The 7100 A and B, which are built for normal capacitors. I can charge them up to 11 volts. I have both an I2C and an SPI version. That's A versus B. The 5100, I also have a I2C versus an SPI. That's A and B. And remember, that device was built for supercap design. So again, I've got 4 different variations depending on the voltages, the power, and really the space constraint that you have available to help you select exactly the right device. But they all do the same thing. They take that coin cell battery and they optimize it for the types of applications where you're transmitting bursts of information, RF energy. Every once in a while, any 4 of these devices will allow you to gain that efficiency.
Okay, that's clear. Now, Tom, could you go back to the standby active cycles and explain how that works? I'm sure our audience would love to hear how these ICs are optimizing the power as well.
And that's really a good point. Let's look at a little technical details now to see exactly how this part does what it's doing. So this page is showing you on the left side the voltages and the currents of the capacitor and the application in the battery itself, and then we're seeing some oscilloscope traces on the right side of it. When I first turn this device on, there's no energy stored in the capacitor. There's no water in that bucket at this point. So typically that capacitor would take a lot of current to begin charging, and then as it charged, it would take less current over time. That's what that first chart is showing you there. However, we don't want to do that to our battery. We want the battery to stay at a predetermined load. We want to set it for only 2 milliamps or 5 or 10 or whatever number we want based on our equation. So as far as the battery is concerned, the Nexperia battery booster says, I'm only going to pull energy at 2 milliamps or whatever the number is to charge the capacitor up. So I've already gained some efficiency. I'm not killing the battery by trying that typical startup current required to charge a battery in the first place. Now, once the capacitor's been fully charged, I now can dump the charge out of it. When I typically would have connected the load to the battery in the past, I would have seen a huge load and the voltage would have dropped on the battery itself because of its chemistry on board. Not with the battery booster. The battery itself doesn't see the load of the application. It's all coming out of the capacitor. So as far as the battery is concerned, it says I still only see 2 milliamps of draw. I don't see anything else at all on it. So the circuit itself, the Nexperia battery booster, provides all the power that's coming out on it. So the voltage doesn't change on it in particular. What's interesting, though, is that suppose the capacitor doesn't get totally discharged on it. Suppose the battery doesn't get totally discharged. I've got energy left inside that battery that I can use for the next cycle. That is where the optimization, where the intelligence of the circuit comes on, is that it knows how much energy it put into the capacitor. It knows how much it put out to the end circuit itself. So the next time, it doesn't have to charge as much information onto it. So that's really the benefit of the optimizer on board. And that's what we look at on this second page then. There's still energy left in the capacitor itself, so I don't have to charge it as much. And over a number of cycles, the optimizer inside the battery booster says, hey, I see that every 5 seconds you need 100 milliamps of current output on it for so many microseconds or milliseconds. It can watch that current. It can say, hey, I don't need to put as much water in the bucket anymore because I know I'm never going to empty it out. So it optimizes itself over time so that there's exactly the right amount of water in the bucket to get the kids exactly the right amount wet as often as they need it in the circuit. It's a totally adaptive system that gives you the capacitive discharge and it modifies it on the fly. It learns to make sure that you're always providing exactly the right amount of energy, no more, no less than what your end application needs.
Cool. This seems like a great solution, Tom. Now, where can it be used to extend battery life? I'm thinking some IoT sensors.
And that is a great application because we've talked about both consumer applications as well as talking about industrial applications. Frankly, there's more industrial applications out for these batteries than you're probably used to. So, one of the first places where you would see that is anything where you've got a circuit that sits for a long period of time and then needs to burst information out. That is the definition of IoT, the Internet of Things sensors. So, temperature sensors up inside a building, a temperature sensor which is stuck in a pallet of frozen fish on the back of a truck, which is going from San Francisco to Washington, D.C. Those are applications where it really fits in. So the battery booster allows you to get higher boosts of current than you could. Remember, if I just have a battery on it directly, I want to make sure that I keep the current low. If I have a battery booster on board, I can transmit much more energy. I can transmit it further. I can transmit longer amounts of information, more details about what the temperature of the frozen fish is. I can send it every 5 minutes instead of having to wait every hour to make the battery last. So it gives the designer of the system way more flexibility on what that IoT sensor is going to do. How long, how much power, how much data I want to communicate. I've got way more options available than I would if I'm limited to just being connected to the battery itself. Another application example is, hey, the one we've talked about is your key fob, which is actually not just transmitting data in the UWBs. It's not just transmitting data when you press the lock or unlock. It actually is monitoring and it's talking back and forth between the key in your pocket and your car in the parking lot to establish that communication. There's a lot of communication there all the time, which is that same thing, relatively long periods of not doing anything, and then bursts of a lot of energy to transmit the data. Do you just want the car to know that you are near it when you're 5 feet away? Would you rather have it that the car knows you're coming up when you're 100 feet away from the car? That requires more power. If I have a battery booster, I have more power available to add features onto that key fob that I normally wouldn't be able to do. So, another good application for this that lets me extend the features of the application itself.
Excellent. Now, Tom, how can my audience start using this technology to extend the battery lifetime of their products they're designing?
And that's where we want to make it as simple as we can. So we want to show you the evaluation board. It's called the NBM 7100 or the 5100, uses basically the same device and same layout. This is a single board designed to help you design your new application. Let's take a look at it. Little board, a couple inches on each side, pretty nice and neat. In the upper left-hand corner of it is a USB interface to your PC. Now, this device has on board an I2C or an SPI interface. Well, that's a little more hardware specific. Everybody's got a laptop, though, that talks USB. So this board is meant to plug directly into the side of your laptop. So the minute you get it, you can plug it in USB and start talking to it. So communication's on board. Of course, there's room for a battery on board, so you can take your CR2032 or whatever battery you want to play with and actually put it in the circuit. This isn't just a software simulation. We're actually going to run real tests on a real battery for your application. On the bottom then, we've put a number of storage capacitors on board. You can change them out if you like. These are ones we recommend because they seem to be optimized for the types of applications we've seen, but change them if you like. On the lower right-hand side, we've actually built an adjustable load center. Suppose your end application isn't done yet, or you're not really sure, do I want to transmit 100 milliamps every 10 seconds or 50 milliamps every 20 seconds? You want to play around with the numbers? We've put circuitry on board already so you can put adjustable loads on it and then see how the battery performs if I take small amount of current over long periods of times or high amounts of current over short periods of time. It lets you play with it. And finally, once you've done this evaluation and you say, hey, this is the capacitor, this is the timing, these are the pulses that I want, in the upper right-hand corner of the board, there's a little piece you can snap off. It has another one of the NBM 7100s or 5100s on board. You can actually take it, there's little holes on it, solder it into your end application, and now you can actually run the board itself. So everything right out of the box. Plug it into your PC, start playing around with the interface to the device itself, start playing around with the optimization, play with different output power, different input currents, work all those out, and then ultimately build a board yourself that plugs into your end application, and you're ready to see how much efficiency you're gaining from our battery booster.
Excellent. This is exciting, Tom. Now, where can we buy these products?
These boards are available right now, both the chips and the evaluation board, available on Mouser. Go to their site and look up the battery booster, the NBM 5100 or 7100. You'll find it there directly. Again, both the chips themselves as well as the evaluation board. Get one and start playing with it right now. And finally, one other part I want to put in here is what might be the perfect companion. In this presentation, we spent time on how to get energy out of these batteries efficiently. Wouldn't there be an interesting device that could put energy into a battery efficiently? Maybe not the same battery, but a rechargeable application. So I'd just like to say a quick word about our energy harvesting device, which takes energy which is free from solar power, from kinetic energy, from thermal energy, gathers it up a little bit at a time over a long period of time, and then puts it into a capacitor so you could take the energy out all in one mode. So all the things we've learned about capacitive discharge and about DC to DC conversion, imagine it on the other side where I'm gathering energy from nowhere, long period of time, then having it available to do similar type of application. They're kind of two different sides of the same coin. Both of them really set for maximum energy efficiency, whether I'm gathering energy or whether I'm taking energy from that coin cell battery and using it in my end application.
Fantastic. All right. Well, Tom, this has been a super cool topic today. But before we go, can you recap your main points for me?
So the Nexperia battery booster was built to extend battery life up to about 10 times. It's going to vary depending on your application, but that is our target. And we're finding end customer applications where 10 times the life of the battery means they never have to replace the battery for the lifetime. So going back to our title screen again, you may have an application where you will never have to worry about the battery over the lifetime of your product itself. The battery is going to outlast what your device is designed to do. It also gives you up to 25x increase in peak power to your load. You're not limited by how much the battery wants to put out. You determine how much power you want to put into your end application, which gives you a lot of flexibility on how far you can transmit, how much data you can transmit, how long you can transmit. That is all available and it's adjustable. You're not limited to the battery itself. The good thing too is that it reduces the number of coin cells that are used. The ones that you discard because they did burn out, the ones that are not burnt out yet, but you replaced them probably before they should have. It gives you a lot of flexibility into it. And hey, it's good for the planet. Do we really want to put 78 million of these batteries into the garbage every day? Let's find a way of making these batteries more efficient and do something good for the entire Earth. And it's ready today. This is not something we're dreaming about doing. The evaluation board and the samples are available now. Go to Mauser, get those boards, and start playing with how you can make your battery design way more efficient.
I love it. Well, this was super cool. Thank you so much for joining me, Tom.
And thank you, Amelia, for allowing me the time to tell everybody about this new product from Nexperia, the battery booster.
And before we go, you didn't forget to click that link, did you? There you can find even more information about this topic from Nexperia. For Chalk Talks, I'm Amelia Dalton from eejournal.com. For more Chalk Talks, head on over to the Chalk Talk section of EE Journal. You can't miss it, it's right across the top. Or check out YouTube, youtube.com/EEJournal.